Okay, so what we're going to do is go over single replacement reactions. And, okay, let's look at the following reaction. So, here's this chemical reaction we can do. We can take penny, which is made out of copper, and we can put it in this magic liquid. Okay, it looks clear, does nothing special about it. But when you do it, what you'll notice is that it kind of gets darkened at the bottom. Okay, so what? Okay, the liquid will go. So what? One thing you'll notice is when this reaction takes place, and here it is again. So these pennies have been dropped inside this magic liquid, and this is what we end up with. Okay, so the liquid go from being clear to blue, and where there was a penny, there's a shining blob of silver. So there's our silver. You get little shiny, all little spikes of silver. So, and it's real silver. It's honest God silver. Okay. So the copper has disappeared. So it's gone away, and the silver has taken its place. Where did it come from? Where the silver came in here from nowhere, and the copper went away. Okay. What's going on? Okay. Just can so it looks like you can turn copper into silver. All right. Transformation or transmutation it used to be called. Well, you can't do that. But let's talk about it anyways. So this particular thing is, so if I took anyways, it's kind of cool. So if you take 1 penny and drop it in here, so this is 1 penny, and after you get done with it, you actually have $5 of silver. Okay, so that's a 500 times gained in my money. Right. So think about it. If you took 10,000 pennies, which is $100, and you put them in this magic liquid, you'd end up with $50,000. That sounds like a pretty good idea to make some money. So usually I tell my class, tell you guys, just bring me $100 pennies, and I'll make you $50,000 of silver, and you can go take it to the jewelry store and trade it in. They'll give you $50,000. Well, not really. Okay, so let's think about it here. So the reaction kind of goes like this: I take solid red copper penny, I add it to my magic liquid. So here it is, my magic liquid, and it produces a shiny solid silver. And it's silver. It's 100% silver and a bluish liquid. So I'm going to write that out. So solid copper plus magic liquid, it gives me solid silver and a blue liquid. And maybe the blue liquid's lost its magicness. I don't know. So where did the copper go? Okay, here there's no copper over here. Okay, and where did the silver come from? All right. So the copper turned into silver. Okay, like I said, they used to call that transmutation, and no, we can't do that. All right. So remember the law of conservation of matter. Matter cannot be created, destroyed. Well, the copper can't just disappear. It just can't. All right. It has to be somewhere. We're missing something, and the silver just doesn't appear. We're missing it. It must be there, and the copper must be there as well. And we're just not seeing it the way we think we see it. Okay, so the magic liquid is the key thing here. So the magic liquid is called a solution. And a solution is made of two parts: a solute, a thing that gets dissolved, and a solvent, the dissolver. In this case, uh, this is a silver nitrate solution, where the solute, the thing to be dissolved, is silver nitrate, and the solvent is water. So before we even do the experiment, we have to make the solution. We have to put silver nitrate into the water. This is real simple. You just take some solid silver nitrate crystals, which looks like a table salt. By the way, all ionic compounds are solid crystals um, when they're pure. And you put it in water, and it dissolves, and it forms a homogeneous mixture. Remember what that is. Um, it just looks like all one substance. So solution is a homogeneous mixture. You just can't sell the silver nitrate anymore. All ionic compounds dissolve in water. For instance, if you put table salt in the water, stir it up, it turns into a homogeneous mixture, and more specifically, it's a solution of sodium chloride plus water. Now, we won't be going into that uh, for this class. You just have to know what a solute is, and what a solvent, and what a solution is. Okay. Okay, so what you have to do is first of all make up your silver nitrate. You take some silver nitrate crystals, put them in water, stir them up, and get them dissolved. Okay, so now what we can do is rewrite this description. So we have our solid copper, which is our penny, in our silver nitrate solution. Drop it in there, and what you produce is solid silver and is clear blue liquid. So what's missing is the copper and the nitrate on the product side. So where are they? Well, they're right here. Okay, so this is the copper and the nitrate. So the liquid turned blue because now copper has moved from being a solid, which is really kind of cool, to being a liquid. And when it does this, it turns liquid blue, and the nitrate is still in the liquid. So I think this is really kind of cool. You have a solid copper, and it turns into a liquid. Okay, and that's really kind of cool. I mean, if you take a penny and hold on to it, it's solid. But when you put in this magic solution of silver nitrate, it's not solid anymore. It's actually part of the water. And the other thing that happens cool is that the liquid silver comes out of the water and becomes a solid. Okay, they replace each other. Okay, so here's the chemical, well, the word equation. Solid copper plus silver nitrate produces solid silver and copper nitrate. Everything is accounted for. So this is the word equation of this reaction. And this is an example of a single replacement reaction. You have a metal plus an ionic compound gives you metal plus an ionic compound. Metal, ionic compound, metal, ionic compound. So, okay, so what we're going to do is that we're going to leave off how these things are, and we're just going to write who they are. So copper, silver nitrate yields silver and copper nitrate. Okay, all right. But before we get into the chemical equation, I want to talk about why this chemical reaction takes place. And, you know, it's going to be kind of a goofy way of explaining, but I think it works. So it's just an analogy. So let's say there's a dance. You remember what dances are? It used to be where people go and like high school dances, stuff like that. So there's this guy named Silver and this gal named Nitrate, and they go to it. That should be go to it. And Silver is dancing the night away with Nitrate. So here they are, Sil and Night. And there's a fellow over in the corner named Copy Per. Here he is over here. Who really wants to dance with Nye. Well, he approaches Sil and asks if he can dance with Nye. And so Sil says, say, what? Okay, obviously taken aback about. Okay, Copy explains he just wants one dance. That's all. Syl is very perplexed, but Copy insists and persists. Finally, Syl. By the way, Syl and Nye are not a couple. They just came to the dance together to dance. Says, okay, but you know what? You just can't dance with Nye. Okay, you got to give us some money. So Copy agrees and he gives Syl some money. And Syl goes and sits down with the money, counts it 100, 200, 300, and Copy gets his one dance with Nye. Well, Copy replaced Syl for this one dance, but it wasn't free. Okay. Well, similar thing happens in this chemical reaction. For copper to take the place of silver to join nitrate, it has to pay with chemical currency. And chemical currencies are electrons. So copper has to give silver electrons to dance with the nitrate. Which brings us back to oxidation and reduction, our oil rig. So copper loses electrons, pays the money, and is oxidized. Silver gets the money, gains electrons, and so is reduced. And what about nitrate? Well, nitrate's just sort of sitting around watching what's going on, actually cheering on, go, yeah, I get some money, I hope you give me some of that money, silver. And so nitrate is called the spectator ion. So let's actually look at what's happening here using the chemical equation. It's nice to come up with a little pretty story that you can think about. But let's see how it actually works in terms of our chemistry. So we're going to look at our word equation and our chemical equation. But before we do that, let's make sure that we sort of get an idea of what's happening with copper and silver. Copper, before the chemical reaction, has 29 protons and 29 electrons. It's uncharged. It's neutral. Okay. So it has a net charge of 0. So what we do is we write it like this right here. Okay. Okay, this is before it loses its money. Then what we need to show is silver, after the chemical reaction takes place, goes from lacking money to gaining money. So when it starts, it's Ag plus, and then after the chemical reaction, it's no longer missing electrons, it's gaining electrons. So one way you could think about it in terms of the story is maybe silver paid some money to get into the dance, and copper paid the amount of money to get in, paid silver's money to get into the dance. So whenever you see an element all by itself, you can give it a 0 charge. So it'll be like Ag 0, Cu 0, magnesium 0, sodium 0. If you see them all by themselves, not in an ionic compound, then you always put a 0 up there, because really key thing here is it has no charge. And this is what I wanted you to do for make sure that for you do the charges when you do the chemical formulas. So let's use your magic skills, your name the formula skills, and be able to take names to formulas. Okay, so first thing you write down is the name. We know that name of so this is the word equation. So what we want to do is now translate to word the new chemical formula. So copper all by itself, Cu, no charge. So don't put 2 plus. Okay, only in ionic will we do the 2 plus. We'll see that in a second. Silver nitrate, well, you should be able to figure that out from what we did, the names of the formula. So silver is Ag plus, nitrate is NO3 minus. Okay, they have the same charge, so you don't have to crisscross. So you're done. Okay, silver all by itself is Ag0, and then you have copper nitrate. So you put down copper, which now has 2 plus charge. It's an ionic compound. Nitrate is NO3 minus. Crisscross charges. Put a 2 here and a 1 here, and you get that. Okay, so you got to do that. So you don't worry. Okay, so now let's look it over. Notice it is in balance. Okay, you have 1 copper here, 1 copper. Don't worry about the charges. Just look at the number of carbons, coppers. There's 1 copper here, 1 copper here. There's 1 silver here, 1 silver here, 1 nitrate here, and 2 nitrates over here. Okay. One thing to notice about polyatomic ions is we treat this whole molecule as one thing. We don't break it up into an N and 3 O's. Okay. Technically, this guy over here means you have 2 N's and 6 O's. Okay. Okay, when you split it apart like that, it gets real messy. You could notice that the NO3 stays the same on both sides. So just balance the NO3 minus. Alright, so you got 2 of these and only 1 over here. So the coppers and silvers are okay, but the nitrates are. Right, so when you balance the equation, balance the single replacement reactions, what I always do is I start out with the negative ion. Okay, and you'll see we'll do as examples. Okay, so notice is that I have 1 nitrate over here, and I have 2 over here. Okay, so what number times what? So if x times 1 has to equal 1 times 2. Well, obviously that's 2. So I put a 2 here. So I have 2 nitrates. Okay. Alright, next thing you'll notice, which we'll go over in the next slide, is it messes up the silvers. Now I have, because the 2 distributes to not only the nitrate, but the silver. So now I have 2 silvers here. Okay. So I have 2 silvers here and 2 nitrates. I have 2 nitrates over here. So since I have 2 silvers over here, I simply put a 2 here, and now I have 2. Okay. So last thing is check my coppers. So I have 1 copper here, and I have 1 here, and so I'm done. Alright, so let me just show you how I kind of explain it with my classes. So first thing I do is I start with negative ion, so I have a 2. So what I do is I go over here, and first thing I do is I put a 2 here. So first step is I need 2 NO3s. Okay. Alright, and then second step is now I need 2 AGs. So second step is 2 AGs. So I put a 2 here. And then the third step, I count my coppers and their equals. Okay, right. So one, step two, and okay. So now let's look at what happens to the substance. So copper goes from Cu with no charge to a 2 plus charge. Now, how did it get 2 plus charge? Because it became less negative. It didn't become more positive in a sense. In chemistry, things either get more negative or less negative. How? Because it lost electrons. And if it loses electrons, it's oxidized. Okay, the silver went from having a plus charge to a no plus charge. So it got less positive, which means it got more negative, which means it gained electrons, and so it's reduced. And the nitrate is a spectator. It's exactly as we said in our dance story. Okay, where does this chemical reaction use? It's used quite a bit. One of the places used for silver plating. So it's real simple. Most of like cheap jewelry, what they do is they take some copper and they drop it in silver nitrate, and you got silver. This is how they used to make mirrors. This is how they make electronics. Also, it's an elementary battery because what happens is that the copper, when it gives off the electrons, if you put a wire in the solution with some sort of light bulb or some sort of source that you want to have work, uh, it'll actually cause the light bulb to light up. So this really is an elementary battery. Okay, so when they first came up with batteries, this is the type of reaction they saw. So single replacement reactions are what really produces electricity in batteries. Okay, so now let's look at another chemical reaction. So let's say I want to build an outdoor deck. All right, you know, in Ohio and the Midwest, it rains quite a bit. Not like Seattle, whatever, but so you're you want to make sure that your nails don't get rusty. So what we do is you go and buy some galvanized nails. No, so let's see why why we do this and why we call them this and why they are rust resistant. So here's a galvanized nail. Well, nails are primarily made of iron, Fe. When they're exposed to oxygen, guess what? They get oxidized, which means they lose electrons. They go from Fe0 to Fe3 plus. Okay, so their reactions and the reaction of rust, and you don't have to do this. This is oxygen, iron, plus oxygen in the air combined to form iron oxide, which is a rusty nail. And the balanced chemical equation is so forth. Okay. Okay, so let's see what goes on here. So the magnesium, when you put magnesium in the iron oxide, the iron will take the electrons from the magnesium and essentially become unrusted. So let's take a look at the reaction here. Okay, so you have your word equation: magnesium plus iron oxide will yield iron. So notice that the iron has lost the oxide, and the magnesium has taken the oxide. So you have magnesium. Okay, Mg, no charge. Then you have iron oxide, which is F. Iron is Fe3 plus. Oxygen is O2 minus, crisscross. And you get Fe3, 2O3. End up with iron. That's not. So iron, Fe, no charge. And then magnesium oxide, Mg 2 plus, oxygen 2 minus. They have the same charge, so you don't have to crisscross. So this is the initial chemical equation. Okay, so let's balance it. Okay, so I always start with negative ion. So I'm going to start with the O2. All right. So here I have 3 O2s. So I need to have 3 O2s on the other side. So there's only one. So 3 times 1. So I have to put a 3 in front to give me 3 O2s. Okay. So I'm done with that. Next thing I do is now I want to fix the magnesiums because I have 3 over here. And so I need to put a 3 over here. Right, and then finally, I'm going to count the irons. Over here I have 2, and over here I have 1, so I simply put a 2 over here, and I got it. And so if you look at what's happening here, Mg goes from Mg0, 2 plus, it loses loses electrons, gets more positive, so it's oxidized. The iron has gained electrons going from 3 plus 0, so it's being reduced. Right. And why is this called galvanized? Because the guy that came up with this idea of electrons moving from one metal to another was Luigi Galvani from Italy. Okay. And that was in the late 1800s. Okay, I'm going to describe this again, how I teach it in class. So I start with my negative ion. I have 3 O2s. So I need to have 3 O2s over here. First step is to get 3 O2s. So put a 3 here. Okay, next thing I now have 3 Mgs. Don't worry about the 2 plus. Second step, 3 Mgs. So put a 3 over here. And then last step, I need third step, I need 2 FEs and put a 2. Right. So the key thing to all these is that I'm gonna give you the reactants, and then you're gonna have to finish the word equation, write the initial equation without being balanced, but it may be balanced, and then balance it if necessary, and then figure out what's oxidized and reduced, just like we do. So let's look at this guy right here. Aluminum plus calcium oxide hydroxide. So to finish the reaction, you just swap the names. The aluminum trades place with the calcium. And again, it doesn't matter. I wrote it up here as calcium plus hydroxide plus aluminum. You can write it the other way around. The initial chemical reactions will be aluminum, no charge. Calcium has 2 plus charge. Okay, OH has a minus charge. So you need to have 2 of them. Okay, calcium all by itself. And over here, aluminum has a 3 plus charge. OH has a minus charge, you need 3 of them. And so that's what you have here. So this is why you have to be able to do names of formulas. Okay, next thing you want to do is balance. So we're going to start with the negative. Okay, so you have, so this one's a little difficult because notice you have 2 OHs over here and 3 OHs over here. So if you notice, common between 2 and 3 is 6. So what you have to do is put a 3 in front here and a 2 in front of here, and now you have the same amount of OHs. 3 times 2 and 2 times 3. Next thing you do is count the calciums. Now you have 3 calciums over here, so you need to put 3 here. Okay, finally, is that do aluminums, you have 2 aluminums, and so you need to put a 2 over here. Okay, again, let's show you how I teach in my class. So I'm going to start with my negative ion of 2 and 3 over here. So what you have to do is, you have to, it's, like I said, it's a little difficult. So just can't fix one, you have to fix both. So what's common between 2 and 3 is 6. So I put a 3 here and 2 here. So first thing I did is ferrix hydroxide. Okay, next thing, it doesn't matter. Let's start over here. I have 3 calciums. So I need to put a 3 here. And then finally I have 2 aluminums, so I put a 2 over here. It doesn't matter which order you do them in. You'll get the same answer. So the key thing is here is this. And in terms of what oxidize and reduce, the aluminum goes from being neutral to losing electrons, so it gets oxidized. Calcium goes from having a positive charge to have no charge, so it gained electrons, and oxygen is the spectator. Okay, so what's next? Okay, we're done with single replacement. Okay, not completely. What we've done is did metal plus ionic compounds. And what you end up with is kind of a new metal, actually, that belonged for the ionic compound, plus a new ionic compound. And there was a transfer of electrons. This metal lost electrons. Okay, and this metal gained electrons. Okay, so what we're going to do now is we're going to do a second type of single replacement reactions.